Thanks for having me. It's a pleasure to present in this event. And today I'm presenting some results, some initial results we've had with the development of a model predictive control for the plasma shape that we are testing in TCV. Some of you might have already heard a bit of this story at the control and operation course here at EPFL in February. Now we have some further results, and so I'm here to tell you a bit of the story. Of course, I'm presenting this, but there's contributions from many people along the way. In particular, for this work, Chris Sangalperti and Maria Topalova was a student working here on this topic specifically, but also people working on shape control at TCV in general, and contributions from Eurofusion and the TCV team. So I'd like to thank everyone who was involved somehow in this effort. Sorry. Okay, so just an overview of what I'm going to present. I will give you a quick introduction to how shape control is dealt with at TCV, with a quick overview of the core magnetic controller and a brief perspective on the recent development on shape control here at TCV. And then I will delve into the topic of model predictive control for plasma shape. I will give a quick introduction. I will try to motivate why we want to have an MPC for the plasma shape. And I will show you some applications and results. And then I will briefly discuss some conclusions and outlooks on the topic, which might also fit nicely with what Georgi was presenting in his talk. So to start with, TCV is known to be extremely flexible in terms of plasma shaping. The name itself means tokamak with variable configuration, so it hints at the fact that it can actually realize a lot of different plasmas. And in standard tokamak operation, still nowadays, shaping is often obtained through careful feed-forward design, and still we have good modeling tools available, as Georgi was telling earlier, and as I will also discuss later. And these allow for reliable design and offline testing of feedback controllers before deploying them to the actual machine. I see we also have Sarah here, who's from Create, which is the group where I was working earlier myself, and they are also experts in magnetic control, and they have their own codes. So this is a field which is quite well, I mean, it's quite explored in the community, and we have different tools to tackle this task. The core TCV magnetic control is based on a set of robust core functionalities, which are pretty standard across tokamaks. And in particular, we have coil current control, we have plasma current control, plasma position control, and vertical stabilization coils. In particular, at TCV, there are some peculiarities, and some combination of coils are, let's say, directly plugged to the RZ-IP control channels. So differently from what is proposed, for example, in ITER, where you basically have a coil current controller and then you give references to the coils. In TCV, you are basically directly plugging these channels to the voltages applied to the coils, or at least to the current derivatives requested to the coils, which makes the analysis of the tools a little bit less straightforward, but it also makes the response a bit faster. So it was a design choice that was taken in the early phases of TCV operation and that we have kept so far. Of course, since we are doing this, we are not controlling all the currents. We are just controlling the currents in an orthogonal space, which doesn't affect the directions that are used to control the core quantities, such as plasma position and currents. So here is an overview of the core TCV controller. The structure is pretty simple. There's a classic coil decoupling plus, as I said, let's say basic position and current control. So here I'm highlighting some of these blocks. The M and R matrices are basically the blocks making up for the current decoupling. There's a set of linear observers based on raw magnetic measurements, which are called the A matrix here at TCV. And then there is a multi-input, multi-output PID controller that, again, takes these observers, computes errors on these quantities, and gives, let's say, requests in terms of the derivatives of the current, which are then actuated through this decoupling block. The advantage of this structure is that there are a few moving parts. The M and R matrices are basically physics-based. You don't need to invent anything here. The observers are also physics-based, and there are routines to obtain them. And basically, you just need to find suitable gains for these control channels. which are in a multi-input, multi-output structure, but are mostly decoupled channels at this point. So the analysis and design of this controller is rather straightforward with standard control engineering tools. This works reliably in most cases and has the great advantage of being easy to set up and adjust for machine operators, who are the ones that ultimately have to deal with these tools every day. So we want to have something that is as user-friendly as possible for them. And also, it was extensively tested over the years. I mean, the first version of this controller was put in place in the 90s, and what we have now as the core magnetic controller is quite close to that. So it's something that is very robust and reliable, that works in most situations, and that we really know well how to deal with. And again, we have tools for feed-forward plasma shaping at TCV. As we say, plasma shaping is often obtained in tokamaks through careful feed-forward design. And at TCV, this is done with the FBT code, which is part of an open source suite of codes, which is called MQ, the MATLAB Equilibrium Toolbox. And this is one of the lines of research that we are pushing forward here at the lab. So if anyone is interested in testing these codes, you can just ask access, and they are freely available, especially for research purposes. Here is an example on a, let's say, example magnetic configuration. Basically, what FBT does, it allows the operator to specify a set of points, which can even be desired contour points or hard constraints, like X points where the field is forced to be 0. And then it solves the Grad-Shafranov equation to fit a solution to the requests of the operator. We have also a graphical interface for the users to play with this. And basically, this is the tool that is used before every discharge to design the current waveforms that go into the machine and allow to obtain the desired configuration. But for feedback plasma shaping, as we said, there are good modeling and simulation tools which we can use to design feedback controllers. Some example of these are the FGE or FGEL codes in the MQ suite we have here. There's CreateL or CreateNL by the Create group, and Sarah will probably tell more about these. There's Toxis by General Atomics. Now I've learned there's this FreeGS suite from UK AEA. There's the NSF simulator that Georgi was presenting earlier, and many other codes. Two main points regarding the design of shape control is that these kind of controllers are expected to deal with very different configurations, especially in a place like TCV. And classic designs for shape control are tailor-made for a target plasma. Think of the XSC, use the jet. You take a configuration, you usually linearize around the configuration to get an intuition of the behavior of the plasma, and then you use that model to inform the control design technique. We also had a list of nice-to-haves when we started this work. So in general, shape control should be mostly automated, because since it's, again, tailor-made for the specific configuration you have, you don't want the user to be messing with the parameter before every discharge. You should have some pipeline that basically takes design parameters and gives you something which is reasonable enough. And the set of parameters which is exposed to the operator should be as small as possible. It should be highly reliable. Again, it should give reasonably good performance on most scenarios with the lowest possible effort. It should be easily reconfigurable in between shots. And I would say that this is where most AI approaches still fail today, because they usually take time to be retrained if something goes wrong, and they are not really at the point where these tools are general enough to be used for day-to-day operation. Of course, maybe we'll get there sometime soon. And also, the controller should be well integrated with the shot preparation tools, ideally with basically the same interface that the operator sees when he's preparing a discharge. TCV has long tradition in plasma control research. The first effort dates back to the 90s. For example, there's a paper, again, by the Create team, where they were trying to use an H-infinity formalism to control some some descriptor of the shape, such as triangularity or elongation. This was a pioneering attempt which relied on the old DPCS control system, which is now not operating anymore. There was very nice work by Hemang Anand, who I think is now at GA, where he basically redesigned shape controller from scratch. This work did not reuse the existing architecture, so it was sort of a parallel track with respect to what is used in, let's say, standard TCV operation. So in the end, I mean, mostly due to time limitation, this never really was merged into the, let's say, the standard workflow of TCV. And of course, there was the Nature paper that was also cited in the previous talk regarding reinforcement learning, which provides a very flexible tool, but which was not designed for day-to-day use, as I was arguing before. So the approach we adopted more recently, that was presented at a conference last year and is now being accepted for publication in PPCF, is what I call the onion scheme shape control, which is basically a PID-based hierarchical architecture, which keeps the core magnetic control of TCV and builds on top of it. And so the shape control gives references to all the channels of the core magnetic controller I was showing you before, including currents, but also plasma position and also plasma position actually. In TCV, the IP channel is decoupled from the magnetic configuration. So in this case, it's mostly plasma position. Note that this is a quite common approach in tokamaks. As I was discussing in the beginning of this talk, in many designs, we have a coil current controller, and then we have external loops such as position or shape, which provide the references to the currents that are then tracked in real time. And often, this is not the case at TCV, but it's the case in bigger devices such as ITER, for example, or EAST. The vertical stabilization has a dedicated actuator which takes care of stabilizing the plane, but it's not involved in position or shape control. The pros of this approach are that the procedure is fully model-based. We have a model of the core controller and a model of the plasma based on the FGEL code, and we can automate the design of the shape control as much as possible. The core magnetic control is, of course, ready out of the box. We say we have this architecture which is extensively tested throughout the years. And we are still using that. And also there's no need in particular to deal with the vertical stabilization of the plasma, which is one of the most delicate loops in plasma control. The cons of using this, let's say, nested architecture is that the performance is slightly slower than what is technically achievable with a direct plug of the control channels to the coils. This is still acceptable for typical shape control timescales, and for, let's say, situations where faster response is required, we have other techniques that we are exploring to make things more aggressive in terms of control performance. For our design, we chose to adopt an isoflux approach, which is slightly less interpretable, but faster to implement with the tools we had. And we also have a way of converting isoflux errors into gap errors in the framework of this NQ suite of codes that we are using. So the way the controller looks, this is just an overview. I won't go into the details. So the top part here, maybe I can point the weight. I think it's here best. So the top part here is the same control architecture that was in my previous slide, and then we add an external loop which takes feedbacks from a real-time equilibrium reconstruction, projects them into quantities that should be controlled by the shape controller, and then has basically a PID plus filters with some pre and post projection matrices that allow to use the control directions in an effective way. So this was the first implementation we had. I'm just showing this as a reference because now from this point, we will move to the substitution of this block here with a model predictive controller. So model predictive control is a quite popular industrial solution in the sense that there's this old saying among control engineers that 90% plus of all controllers in the world are actually PIDs. But recently, MPC is emerging as an alternative paradigm. So for those who are not familiar with it, the core ideas of MPC are using a plant model to forecast the output future trajectory. And you see that here we are actually forecasting in the dashed lines actuators, projectors, and states, for example. Then we find the optimal input sequence according to some objective through, let's say, standard optimization tools. We take the first sample of the optimal trajectory over the horizon we are considering, and we apply it to the plant. And then we shift everything forward by one sample and, let's say, rinse and repeat. We repeat the process over and over at every time step. So why do we want model predictive control? So the first reason to have model predictive control in the context of plasma shaping is that it can handle soft or hard constraints. Sorry, this is a typo. It can handle soft or hard constraints. This could be coil current saturations, limits on requested voltages, plasma wall clearances, for example, or the maximum distance between multiple separatices in the case of multiple X-point configurations, and so on and so forth. So this provides a very powerful way of enhancing or with soft constraints, adding high weights on the violation of some operational limits, or really forcing the solver to pin some desired quantities to the value that they should get. For example, where you don't want to exceed saturations and you want to have like a very, very tight distance between different X points. It has predictive capabilities, which allow to compensate ahead of time for known events, which helps minimizing the lag time when references are moving, and this happens, for example, in response to asynchronous events. So imagine you have a soft landing scenario where you want to ramp down the discharge, then you can sort of adjust in advance to follow the trace as closely as possible. You can use different models also during the same discharge, which provides a way of cleanly switching between one plasma target configuration to another one. And also you can use the additional degrees of freedom to satisfy secondary objectives. And this is something which is really felt in TCV because we have many coils available, and so we can use some of them to achieve other things which are not the main objective of the controller, which is just bringing the plasma close to the reference. And some example of these could be, for instance, keeping the coil currents low or minimizing the injected electrical power into the machine, or for example, handling forces on the structures, things like that. IPC infusion in general is a concept which is not completely new. It has been tested at TCV before for safety factor profile control, and there's a nice work and actually the PhD thesis of a colleague from DIFR, Bert Malgers. It has been proposed for other tasks such as density control or store thermal energy control, also internal inductance and other examples. And MPC-based plasma shape control was also proposed for future devices such as ITER or DEMO. The first work I found on the topic dates back to 2013, also by the Koreate people. There was a group working in Slovenia about this for ITER, and there was a couple of talks in which I was also involved at some point at conferences in the past couple of years. The idea is that in bigger devices, you have slower dynamics, and so you have more time to solve the optimization problem arising from X. While using these on smaller devices might be a little bit more challenging due to the very little time available when you have very fast dynamics to deal with. In TCV, we have, let's say, all the ingredients we need to design an MPC controller. We have accurate models of the plasma dynamics. Again, we can rely on this MQ suite of codes. And as reported in the book by Rossiter on model-based predictive control, you can only control as precisely as you can model. So if you want more accurate controller, a more tuned controller, you need a more accurate model. We have also a flexible real-time framework for fast prototyping and testing. This is called the SCD. And the core of SCD is also open source and was adopted by ITER as their control system. There's a recent publication on this by my colleague Christian Galpetti that recently came out just at the end of last year on field engineering design. And also we can rely on efficient optimization solvers as we are putting our problem in a standard quadratic programming form. And so we have many solvers available. Here I reported some examples. There's the OS2P by the University of Oxford, there's 2P Oasis, Kazadi, the one by the Audis company, and also many other open source implementations that can be used. So the way the controller looks like is something like this. So the part that is highlighted as prediction model is the core hybrid controller, which I condensed into a single block for simplicity. The plant model with the power supplies and the diagnostics and the reconstruction equilibrium code, which provides the desired feedback for shape control. All of these can be embedded into a single state space block. Of course, we are linearizing, in this case, the dynamics of the plasma. And this model can then be given to MPC for like to generate forecasts of the output trajectories, and then to formalize an optimization problem to a preprocessing stage. Then the problem is solved through a QP solver, a standard QP solver. And then the other part we have is a Kalman filter, which is necessary to estimate the current state of the plant. Because as you might already know, I mean, for those who are familiar with tokamak control, the state of the plant is given by all the currents flowing in the machine, including the ones induced in the passive structures, which are usually not measurable directly. So we decided to have an observer to estimate the current value of these states and to use that as an initial condition for the trajectory forecast done by MPC. In particular, we use a reduced order Kalman filter. We have seen that a few tens of states are enough to get reliable enough performance. And we decided to adopt a velocity form for offset tree tracking. This is pretty standard in MPC. Alternatives might be using like disturbance estimation models, but this seemed to work well enough for our purposes. And in the current implementation, we are only implementing coil current constraints, but there's a plan to add other ways of constraining quantities of interest, such as the voltage requested by the hybrid controller, or, for example, again, the distance from the wall during transients to, let's say, for safety concerns. Of course, computational efficiency is key for MPC, as we only have a handful of milliseconds. I didn't mention it in my previous slide, but actually this MPC is running with a 2 millisecond pace, and the optimization problem arising from these has a few tens, so around 50 to 60 optimization variables and a few hundreds of constraints. So it's a decently sized problem. It's not the smallest one I've seen. So we need to be efficient. And the idea here is to pre-compute matrices as much as possible to reduce the optimization problem by using like reduced state representations, or maybe SVD decompositions to reduce the amount of degrees of freedom used by the controller. You can reduce the controller horizon by only optimizing over a subset of the prediction horizon. You can apply constraints at every other step. And you can try to choose your solver wisely, possibly using warm start where possible. So as I'm already at 25 minutes, I will quickly go over some results. The first example I'm showing here is fast shape variation tracking. We took one of the TCV standard configurations, and we asked for a vertical displacement plus a change in elongation. The settling time of the controller is in the order of a few tens of milliseconds, which is quite faster than what we had with PID-based control. There is some residual ringing that you can see. This is attributed to the interaction of this controller with the VS system, and it's currently under investigation. This is probably due to some non-ideality in the way we model the VS circuit, maybe in the power supplies. And indeed, you can see that these oscillations are slightly reduced when we go in the phase where the elongation is reduced, which means that the growth rate is probably decreasing, and hence the vertical response is more gentle, and the oscillations are also suppressed. You can also see that during the displacement, this strike point is moving a bit around, but actually this is not a big concern in the sense that there is a big null point region here. So even if the leg is moving by a bit, the flux error is not that big because the gradient of the flux is almost flat here. Of course, we can enhance the control performance by increasing the weight on this channel, but as far as the control demonstration goes, this is something that is perfectly explained by the theory behind the controller. So it's not the result of let's say, it's not a miscontrol channel. It's a result of how the optimization balances the different objectives. The same scenario is repeated here, but saturating coils. So you see that we fictitiously reduced the saturation limit of one of the coils to 2,500 amperes, while keeping the other ones saturated at 3,500, which is still a lower limit than the actual limit of the TCV coils. You can maybe see here at the beginning that one of the currents starts outside of the saturation limit and is then brought back into the into this region, this safe region. As a response to that, other currents are ramping outside of the 2,500 kiloamps, but they are still limited at 3.5 kiloamps. And you can see that they are never exceeding this threshold. You see that the response during the elongated phase is slightly different. We don't have the fast recovery we had before, but we have this sort of flat region where the error is still reasonably small, but of course we have to trade off the shape accuracy with the constraints that we are imposing on the optimization. And finally, the third case I'm presenting here is adding a secondary objective, which in this case is current norm minimization. In this case, we are keeping the shape steady. We are not changing it anymore, but we are adding current norm minimization as a secondary objective in the optimization process. And here you see a comparison between the baseline case, where the shape is not controlled, and the currents have an RMS below 6 kiloamps. Then we have the black dashed line, which represents the case with control, but without minimization of the currents. And you see that the current RMS rises up to 6.5 kiloamps, sort of. And finally, the dotted blue line is this discharge. In this case, the controller was switched on slightly later, so you will see a bit of a shift. But you can clearly see that the currents start ramping and then are brought back to the levels of the baseline discharge. So in this case, the weight on this objective was not very high, because we still wanted to retain a good accuracy in terms of the plasma shape, but you can of course increase that if you really want to reduce the currents used to achieve the shape, and you are willing to trade them for less accuracy on the plasma control. To summarize, MPC offers a flexible solution for the problem of plasma shape control. We have seen that it provides a good control accuracy. It has an effective way of handling constraints. It allows to exploit effectively additional degrees of freedom, and it has, of course, predictive capabilities which enhance the tracking of moving targets. And also it can be enhanced in several directions. So, of course, there are robust or adaptive formulations of MPC which allow to deal with uncertainties. Constraints can be formulated in a more flexible way, so allowing to deal with different quantities at the same time. We could use AI-informed model or reinforcement learning plus MPC combinations, which are topics which are emerging now in the MPC literature and are, I think, very promising in view of, say, of the task of controlling a fusion plasma and many others point. Let's say the takeaway message here that I think is what I learned working with MPC and fusion is that AI is good, and it's a very flexible and powerful tool to deal with very complex systems such as fusion devices. But I think we also have very reliable control tools which have been developed across the decades. And I think it's the most effective way of dealing with this sort of thing is combining the two domains to get the best of both worlds. So we can have, for example, machine learning informed models which are able to capture dynamics which are more complex to tackle maybe, but you can also have, for example, analytically grounded optimizers which give guarantees on the optimality of the solution and on the handling of constraints and so on and so forth. So I will conclude here, and of course I'm open to questions if any.
Yes, thank you. Thank you very much for a wonderful presentation. And I agree with your last statement about combining conventional and machine learning approaches. Definitely, I mean, in the modern world, last couple of years, we feel like everything, we got AI like a hammer and everything is a nail. We are trying to apply AI everywhere. And of course, there is a concern that we will quickly find limits, and we will quickly find edge cases where, like, we are more equipped with conventional rather than with AI. A few questions I spotted in our Q&A tool. First of all, from Maxim, do you expect the transfer of MPC from TCV-like devices to demo-like devices to be seamless?
I would say yes, for two main reasons. The first one is that actually MPC was first designed for demo-like devices, and then it was transferred to something like TCV. So actually it was the opposite transfer that was more complicated in some sense. But actually the point is that TCV has peculiarity of being a machine with many degrees of freedom and with very fast dynamics. So there's basically, I mean, the optimization problem is a bit bigger and more complex than in devices like ITER or DIMO, and it's also we also have less time to solve it. So from the control perspective, applying MPC to a bigger machine is actually easier than doing it on TCV. The real question is whether we can have a formulation which is robust enough and reliable enough to handle safety critical constraints in a very, let's say with very strong safety guarantees. But this is something that is a bit of a research topic, and I think this can be tested on devices like TCV and then transferred to other machines.
Yeah, sure. Thank you. One more question from Georgi. Kinetics and especially MHD prediction can be time consuming. Is there a clever way to extend MPC for 3D control or for kinetics control?
So for what concerns kinetics control, I think actually that profile control was one of the first areas to be tackled by MPC. I think the size of the problem is not much bigger than the one. I mean, actually, it's usually smaller than what you have for example, shape control. So the real point is whether you can have efficient solvers. For example, if you think about temperature control or density control, there are very efficient codes such as Raptor or Raptance that can be used. And I think if we manage to, for example, inform them in edge cases, for example, with machine learning or with like clever ways of describing the physics we're interested in, then they could be used for MPC, I would say. On the other hand, for 3D control, these may be a little bit more challenging. But I'm not an expert there, to be fair, so I don't want to say to give any strong statement on this.
Yeah, sure. Thank you. And one more question about does MPC controller require real-time equilibrium reconstruction, plasma evolution prediction in several trajectories? And isn't it prohibitively compute heavy?
This was the question we wanted to answer to with this work. And of course, you have to do some compromises. Let's say equilibrium reconstruction typically runs separately from MPC. So right now, for example, we have a real-time equilibrium reconstruction code that runs in a few hundreds of microseconds. So this is perfectly compatible with shape control in this case. I think the real bottleneck is the solution of the optimization problem. Right now, we're using a linearized model, which allows us to formulate the solution as a quadratic programming problem, which has analytical solutions, and even in the constraint case, can be solved quite efficiently. And right now, for the dimensions that I was mentioning earlier, so let's say 50 optimization variables and 500 to 600 constraints, we can run the optimizer with around 10 to 15 iteration in around 1 millisecond. So this is, I mean, this was quite surprising also for us. It was very efficient in the end, the formulation we came with. Of course, if you want to go to nonlinear models and maybe move from quadratic programming to more general convex optimization, then this may be a little bit more time-consuming, and there you will need to find clever ways of making the solver efficient.
Okay, good. And I will stop with questions here. If we get any more questions, I will forward it to you and we discuss how to answer it and how to let people chat with you about some interesting points, because I see people asking. But I would like to switch to Sarah.